we present 360MonoDepth, the first technique for high-resolution 360 monocular depth estimation. 360 images capture the scene around us in a single snapshot. These kind of images are beginning to make their way as a standard in many computer vision fields like VR, robotics, surveillance. Therefore, it is necessary to adapt computer vision methods previously designed for perspective images to 360 imagery. With the advent of deep learning, estimating dense depth maps from a single RGB image has become possible. There exist huge collections of annotated datasets, which enables monodepth techniques to generalize widely. Our goal is to estimate a dense depth map given a single high-resolution 360 RGB input image. However, 360 is different from perspective and existing techniques can't easily be adapted. This is because 360 images are highly distorted at the poles. Additionally, we are interested in high-resolution 360 imagery at 2K resolution or higher, as this helps create more immersive VR experiences. Current approaches cannot achieve this resolution because of high memory requirements. At the moment, there is only limited ground truth 360 RGBD data. This is only from indoor environments. Training a model with the available data suffers from poor generalization as outdoor data is never seen. Existing work on 360 monocular depth estimation directly use 360 RGBD annotated datasets. They try to mitigate the inherent distortion of 360 images by merging combinations from less distorted projections such as a cube map projection, or extract latent horizontal features which assume that vertical lines align with the gravity vector. Nonetheless, they all present common drawbacks: low resolution predictions, up to 1K, and poor generalization capability due to the scarce amount of 360 RGBD datasets. To achieve higher resolutions and better generalization, we directly leverage the performance of state-of-the-art models trained on huge collections of perspective RGBD datasets. The input to our framework is a 360 high-resolution color image. Then, we project the input image into a set of perspective images tangent to the faces of an icosahedron. The tangent images are perspective images with negligible distortion. The tangent images are now suitable to be fed to an off-the-shelf perspective monocular depth estimator, which will output a set of individual depth maps up to an unknown scale and offset factor. Afterwards, we project the perspective depth maps to a rectangular projection. To bring the tangent depth maps into agreement, we perform a global optimization so that every depth map is deformed to align with each other. In this way, they will all represent the underlying scene geometry with the same depth magnitude. Finally, we blend the contribution of each depth map into the final 360 depth prediction. We obtain state-of-the-art results on indoor real data. Note the sharp boundary around the lamp compared to previous methods. In indoor synthetic data, notice the sharp chair boundaries. And outdoor data. Note that our approach does not need any training as we use off-the-shelf perspective monocular depth estimators. In conclusion, we present a modular framework which can benefit from future improvements to both depth estimators and blending techniques. We achieve powerful generalization using off-the-shelf perspective monodepth techniques. And finally, our approach is the first to achieve depth estimates matching the high resolution of 360 input images. Thanks for your attention.